So in section 6, which is the last section of module 6, we're going to take a look at linear programming, which is just another way of saying systems of inequalities where you have more than two. So what linear programming does is it's a method that's used to try and minimize or maximize a quantity given by a linear equation under certain restrictions or constraints. So the constraints are going to be our inequalities. So two very common examples of this are business and industrial engineering. So when I say industrial engineering, we're talking about manufacturing, stuff like that. Let's go ahead and look at our first example. So we have that a company manufactures and sells 2 camping lights. One light has disposable batteries for $5 and a second light with rechargeable batteries for $10. However, due to limited resources, the production of the 2 lights has the following restrictions. The company must produce at least 5 lights with disposable batteries, but no more than 15 per day. The number of lights per day with rechargeable batteries produced must be at least the same as the number of lights with disposable batteries, and the number of lights with rechargeable batteries produced must be no more than $20 per day. How many of each light should the company produce and sell in order to maximize its revenue per day? What is the maximum revenue? So there's a lot of information going on in this problem. So let's just start by identifying our variables. So our first variable, x, is going to be the number of disposable battery lights. And y is going to be our number of rechargeable battery lights. Next, we want to identify our revenue equation. So the amount of money that we're going to be making off of these lights. So we know that you can sell disposable batteries for $5 and rechargeable batteries for $10. So that's my linear equation. So it tells me my revenue for x and y equals 5x plus 10y. And we do not graph our revenue equation. We'll use it at the very, very end, but it is not graphed at this point. The next thing we're going to do is come up with our inequalities that are going to determine our solution region. So that is our second kind of paragraph here. So there's 4 pieces of information that we're going to use. You have to produce at least 5 lights with disposable batteries, but no more than 15. And then for the rechargeable batteries, you can do no more than 20, but it has to be at least the same as the number of lights with disposable batteries. So those 4 statements are going to give me 4 inequalities. So that tells me my number of disposable batteries has to be greater than or equal to 5, but it has to be less than or equal to 15. And my rechargeable batteries, I have to make at least the same amount as disposable, so it has to be greater than or equal to 5, but it also has to be less than or equal to 20. Now I want to go ahead and graph those inequalities in my graph here. And I'm going to go ahead, just label my bottom axis, my x-axis, and then the side my y. Now I need to come up with a scale. So I can have each line represent 1. I do have enough spaces. So I'll go up to 15. So this is where 0 is. So I labeled my scale for my X and Y axis, which is going to be very important because you are going to get to pick it a lot of times to make sure that you can fit your graph. Now I'm going to start graphing my inequalities, which are all vertical and horizontal lines. So I don't have to worry about slopes. So anything greater than or equal to 5. So I have a vertical line going through 5. And then I have to be less than or equal to 15. So the solution is going to be between those two lines. So that's one solution region. Okay. And then for my other inequalities, I have the y has to be greater than or equal to 5, but also less than or equal to 20. So everything in between those are solutions. So when you are trying to maximize profit, what you need to do is find the corners of something we call the feasible region, which are the corners that contain our solution region. So our solution region is where they overlap in the middle. And there are 4 points that contain our solution region. And those are the 4 points of my rectangle here. So those are the points 520, 1520, 15.5, and 5.5. So in order to figure out how many they should produce in order to maximize their profit, I'm going to plug each of these 4 points into my revenue equation. So we're going to start with the point 5.5. So that becomes 5 times 5 plus 10 times 5, which is going to be $75. Then we'll check the point 520, which is 5 times 5 plus 10 times 20, which is $225. Then we'll check the point 15.5, which is 5 times 15 plus 10 times 5, which is $125. And then lastly, the point 1520, which is 5 times 15 plus 10 times 20, which gives us $275. So in looking, obviously I get the most money with this last point. So I'm going to be writing a sentence summarizing how many they should purchase and what their max profit is. So 15 disposable battery lights. And 20 rechargeable battery lights. Should be manufactured. To get a max profit of $275. In our second example, we have that Buffalo Bob's River Explorers rents canoes and kayaks to people to float down the Buffalo River. He has $45,000 to purchase new boats. Canoes cost $600 each and rent for $25 per day, and kayaks cost $750 each and rent for $30 per day. He only has room for 65 boats in his shop. How many of each type should be bought to maximize his revenue? So I'm going to let X be my number of canoes. and y be the number of kayaks. So again, we're trying to maximize revenue, so that tells me R of xy equals, so I want to pick out my revenue, so you rent $25 per day for canoes, and kayaks rent for $30 per day. So that tells me 25x plus 30y is my revenue equation. Now I'm going to start with my inequalities. So it doesn't specify it here, but one piece of information for all of these is that x and y have to be greater than or equal to 0. I didn't bother with it on my previous example because my minimum for x and y were both 5, so they were already going to be greater than or equal to 0. But in an example like this, I do need to specify that x and y are going to be greater than or equal to 0, because I can't rent out a negative number of canoes and kayaks, and you can't purchase a negative number. So we want to restrict our solution region to positive values of x and y. Now I'm going to pick out information to write my other inequalities. So we know that he has $45,000 to purchase new boats. And we know canoes cost $600 and kayaks cost $750. So that tells me 600x plus 750y has to be less than or equal to 45,000. Lastly, we know that he only has room for 65 boats in his shop. So that tells me that x plus y has to be less than or equal to 65. So sometimes the inequalities that we want to graph are going to be linear, not just strictly vertical or horizontal lines. So let's work on graphing these two inequalities. So again, I'm going to have my x and my y-axis. So I'm going to rewrite both of my inequalities so they're in slope-intercept form, because right now they're both in what we call standard form. So I would, for my first one, I would subtract the 600x to both sides and then divide by 750. So I end up with negative 4/5 x plus 60. And for my second inequality, I'm just going to subtract x from both sides, and I get y is less than or equal to negative x plus 65. So that's a lot easier to graph than the inequalities as they're currently written. So these are the inequalities I'm going to graph, along with my x and y greater than or equal to 0, which we don't really shade so much. It just helps us look at just positive numbers. So my 0, 0. Then for my scale on the x-axis, I'm going to skip line. I'm going to start with my first line of 5, and I'm going to skip them. So I'm basically going up by 10. So 5, then 15, 25, 35, 45, 55, 65, 75, 85. So basically, each line is 5. It's just to kind of save some space, I'm only labeling every other one. So for the y-axis, I'm not required to go up by the same scale. I am going to for this one just to make it a little bit easier. So I'm going to start at 5, and then I'm going to skip. So 5, 15, 25, 35, 45, 55, 65, 75, 85. I'm going to go ahead and stop there. I don't need to keep going, because if I look, my y-intercepts are both 60 and 65. So I don't need to keep going in order to make sure my graph is correct. And I just realized I skipped a line, 2 lines. So 35, 45, 55, 65, 75, 85. There we go. So the first inequality I'm going to graph is the y less than or equal to negative 4/5 x plus 60. So I'm going to start my y-intercept at 60. And then because I went up by the same scale on my X and my Y axis, I can go down 4 and over 5. And then I can keep doing that. Then I'm going to connect my points. And then my inequality is less than or equal to, which means we want to shade everything below that. And this is where the greater than or equal to 0 for the X and Y comes in. So I'm only interested in the numbers above 0. Now for my second inequality, the Y less than or equal to negative X plus 65. So my Y-intercept is going to be 65, and my slope is negative 1. So I go down 1 over 1. And again, because I went up by the same scale, I can do that. And we're going to connect our points. And its solution region is also the region below. Now we want to find the corners of our feasible region, of which there are 4. So 0, 0 in this situation is always one of the points. Then to find your other points, you go straight up until you run into y-intercept, which in this case would be 0, 60. You go to the right until you run into an x-intercept, which is 65, 0. And then you use the intersection point, which is a little bit difficult to see on this graph, but if you use Desmos, it is the point 25, 40. So these are the 4 points that I'm going to check to see which one maximizes revenue. I'm not going to actually check 0, 0. I don't expect you to either, because obviously if I don't sell anything, I'm not making any money, so it's not going to maximize revenue. So I'm going to check the points 0, 60, 65, 0, and 25, 40. So we'll have 25 times 0 plus 30 times 60, which gives us a revenue of $1,800. For our next point, we have 25 times 65 plus 30 times 0, which is 1,625. And then lastly, we have 25 times 25 plus 30 times 40, which gives us a revenue of $1,825. So this last one is going to maximize our profit. So we can say that Bob should purchase 25 canoes and 40 kayaks to get a max profit of $1,825. So please let me know if you have any questions about linear programming, especially when it comes to writing a revenue equation. We will see cost equations as well. So the only difference between a revenue and a cost equation is instead of saying R parentheses XY, you say C parentheses XY, so you know it's cost. Writing your inequalities, and of course graphing them, finding your points of your solution region, and then checking those.